Hello everybody, welcome back to another Coding with Tyler video. Today we're going to look at a topic that you don't necessarily need, but it is very valuable to know, and it's something that I think helps a little bit into just seeing how functions work a little bit more, and we'll be able to delve a little bit more in depth with them. And also, you know, show some cool stuff that we can do. There's a lot of cool stuff you can do with what I'm going to show you today. And we'll do a couple examples at the end of the video. I do want to just say this Sunday will not be an example of this. We'll do examples in here. On Sunday, we'll just have a little one-off before we get into some little intricacies of Python doing some more cool stuff. So don't expect to see more recursion, which is what we're covering today. On Sunday, it'll be some new stuff. So a little bit of a schedule change for this week, but that is okay. So what is recursion? Obviously, this is the topic of today's video. Let's get into our coding screen here. What is recursion? And I'll type this out for you. What is recursion? So recursion is the process of calling a function inside of a function. Process of calling a function inside of a function. So what does this mean? Let's say we have a function, and it's just going to be a simple one. It's going to be an add function, and we're going to pass in x1 and x2, and then we're going to take x1, and we're going to make x3 a value. You know what? We'll just return x1 plus x2, and it'll be literally as simple as that. Is that okay? Are we fine with that? Because I'm okay with that if you're okay with that. We're returning x1 plus x2. This is a function as we know it, as we've used in previous videos. Everything's fine with it. No problems whatsoever. A-okay. How can we make this a recursive call? Okay? Instead of saying return x1 plus x2, let's return add of x1, x2, and then we'll just like increment these by 1. Okay? So what exactly is this code doing? I'm going to tell you right now, nothing of value. This is literally an example to show you that this is a recursive call. This is basically going to infinitely recurse, just showing that we're going to add 1 to these things, and it's just going to continue to return and return and return until my computer explodes, essentially. And Python will tell you when your computer explodes. I have to actually run this thing. So we'll make x equal 1. We'll make y equal 2, and then we'll do add of x well, I mean, we could have just passed in 1 and 2, but we'll do add of x and y. This is basically just going to say, Tyler, your computer is about to crash. And I'll pull up the little thing here so you can see it. And boom, yeah, it did not like that in the slightest. You can see right here, we got all kinds of boatloads of errors. And you can see right here at the very bottom, it says maximum recursion depth exceeded. This means that this just recursed forever. And that's exactly right. We don't have a statement saying to ever stop. It's just going to continue to add and add and add and add and add. So that's recursion. That's literally what this entire video is going to be about. And I can see you right now. You're sitting here, you're going, so don't do it. You know, why bother doing this? What's the point? Why would I ever use recursion? Well, thank you for asking. Recursion is incredibly valuable, and there's a lot of problems that are easier to solve using recursion than using iteration. And iteration, just to get some definitions in here, is whenever we use while loops or for loops or do while loops. I know we haven't covered for loops or do while loops yet, but we will. We'll maybe cover them in the next video, since next video will be a bunch of random little stuff. That's all iteration. You can, most of the time, and I say most of the time, you can do it every time. You can solve a problem with iteration or recursion, whatever you choose. But there are many, many times where using iteration is significantly easier than using recursion, and there's a lot of times where using recursion is significantly easier than using iteration. So I can tell you right now, you're gonna hate recursion. It's tough to wrap your head around, and I hope this video will help a little bit. Iteration is easy. While this, do this, okay? Iteration is simple. Recursion takes a lot of brain power to figure out, and it took me a really long time to figure it out. So if you're walking away from this video completely confused of what's going on, don't worry. Okay? Recursion is a tough topic to wrap your head around. I don't like it. If I can use iteration, I use iteration. I suppose I should keep this information in here. But there are times where using recursion is significantly easier, and I'm sure that you will see those times eventually. So let's talk about a couple examples where recursion is better to use than iteration. Who here has heard of the Fibonacci sequence? I expected someone to raise their hand, but instead, I can't see you guys. Somebody here has heard of the Fibonacci sequence, and surprisingly, the Fibonacci sequence is actually a recursive function. You didn't know that, did you? So the Fibonacci sequence, for those that don't know, it's essentially a sequence of numbers where the first number is added to the second number, and that gets you the third. And then the second is added to the third, and that gets you the fourth added to the fifth, get the sixth, and you go on and go on and go on. And this sequence, the Fibonacci sequence, occurs all over. In nature, in building, it's literally everywhere. It's used to derive what we also know as the golden ratio, which if you look at your computer monitor, a lot of you are probably rocking a 16:9 computer monitor, whether that be 1280 by 720, 1920 by 1080. The golden ratio comes out to be around 1.6. And if you look at 16:9, 16:10 is around 1.6. So back in the day, a bunch of people, I mean, they figured out the golden ratio because it's what's most pleasantly appealing to the eye. And they started to make a ton of paintings that followed this ratio. And I'll throw up like a couple of pictures of paintings in the golden ratio. But then they found that this ratio occurs all over in nature, and it's using the Fibonacci sequence. So just to show you what the Fibonacci sequence is, you start with 0. Here, we'll call this Fibonacci sequence. And this isn't a math course, so I'm not going to go into big depth about the Fibonacci sequence, but we will do the code of literally what it's doing. And I'm telling you that this is 6 lines of code. You're going to be really impressed with this. So it starts with 0, and it starts with 1. Okay, those are kind of the base cases, but then we go into the adding. So you take the first number, you add it to the second. So the third number of the Fibonacci sequence is 1. I don't know why I typed 3. Then you add those two. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 8 plus 5 is 13. 13 plus 8 is 21, and then this goes on and on and on, doing the Fibonacci sequence. I think that's right if I'm doing the math in my head, except it's actually totally not. That's 34, and then that's 55. So there, 55, right? Yeah, 21 plus 34, 55. It's hard to add in my head. So that's the Fibonacci sequence, and this goes on forever and ever and ever. It just keeps on going. So we're going to use a function, a recursive function, to figure out a number of the Fibonacci sequence. So let's define this as, we'll just call it Fibo. Sound good? Fibo. And then we're going to pass in a parameter. We talked about this in the last video. We're going to pass in a parameter that is the number in the sequence that we want. So if it's one little thing that you'll learn as time goes on, and we'll cover this more when we start talking about lists. Everything in computers, the first element is 0, and then the second element is 1, and then it goes on from there. So if we send in 0 here, we should get the first number of the Fibonacci sequence, 0. If we pass in 1, we will get the second number, which is 1. We pass in 2, we get the third number here, which is 1. Pass in 4, or 3, we're going to get the fourth number here, and so on. So what is the Fibonacci sequence code? I'm going to write it here and just try to follow along, and then I'll explain exactly what it's doing and we'll walk through it. So if n equals 0, then we just want to return 0. If n is equal to 1, then we just want to return 1. Otherwise, and we want to have this be an elif here, and then otherwise, we want to return fib of n minus 1 plus fib of n minus 2. Okay, and by fib, I mean Fibo. Sorry, I forgot that I changed it. So what is going on here? Let's get the first number of the sequence, okay? So we're going to pass in 0 because it's the first number here. So 0 is going to be Fibo of 0. So it's going to bring in, it's going to say, so if n is equal to 0, return 0. That's pretty straightforward. That's going to return 0. We have what we want. Okay, let's do the second one. So we got n is going to be equal to 1 because it's the second number here. So if n is equal to 0, return 0. It's not. So elif n is equal to 1, return 1. Okay, cool. We got 1. That's perfect. That's exactly what we need. Now we're going to do n of 2. N is equal to 2, okay? So we pass in 2. If n is equal to 0, return 0. It's not equal to 0, it's equal to 2. Elif n is equal to 1. It's not equal to 1, it's equal to 2. We already talked about this. So else, return Fibo of n minus 1 plus Fibo of n minus 2. So Fibo of 2 minus 1 is Fibo of 1. So Fibo of 1 we just did. That's going to be 1. So 1 plus Fibo of 2 minus 2, which is 0. So that's going to be 0. We already know that. So it's going to return 1 plus 0. And if you look right here, it's 1. So 1 plus 0 is 1. That did everything correctly. Let's walk through. This is going to get really, really complicated here. Let's walk through Fibo of 3 here. Okay, so we passed in 2. Let's pass in 3, and we should get 3 as our answer, and it's going to be a little bit more complex here. So we pass in 3. We know these aren't going to go, so we go to here. So return Fibo of 3 minus 1. So then that's going to be 2. So then it's going to go back here. We're going to go, okay, so n is equal to 2 now. We go down, we get to here. It goes, okay, so 2 minus 1 is 1. We go to here, we get 1. So this Fibo of n minus 1 from the original Fibo of 3 minus 1, this is going to be equal to 1. I think. Did I just say that wrong? Look, walking through recursion is insanely difficult without being able to write it down right now. So you know what? I'm going to attempt to type this. So n is 3. Fibo of 3 minus 1 is Fibo of 2. So Fibo of 2 is 2 minus 1. But, oh, geez. But I forgot that we have to do this part of it as well. I'm not going to walk through this because I'm telling you right now, it's going to hurt my brain. I'm going to end up making a mistake. It's easy to write it down on paper, and you want to do this using a tree branch setup. And you know what? I'll throw on the screen right now. I'll make a branch setup here so you can kind of see what's going on. But it gets complicated, and this is why recursion can break your brain a little bit, because you're calling that over and over again and trying to see what's going on while you're calling it over and over again. And this is going to get insanely complex as we put higher values of n into the function. And you can see, so let's do something here. Let's call Fibo on 5. So this should give us 0, 1, 2, 3, 4. Fibo of 5, it'll give us one of those numbers up there. We run this. It did not give us anything because we're not printing out what we're getting. So print Fibo of 5 because it's going to return a number for us here. So Fibo of 5 is 5. There you go. So it's that value right there. If we do Fibo of 6, this should return 8, and it does. Fibo of 7 is going to return 13, as we know. Fibo of 8 is going to do 21, perfect, and so on and so forth. So it's pretty fast doing this right now, but as you get more and more recursive calls, it's going to strain your computer more and more. And this is, it's called time complexities, and I'm not going to go into time complexities in this video. We might cover those in a future video if we do some sorting algorithm type stuff, which I think is reasonable for us to do in the future. But this Fibonacci sequence and most recursive calls have a really, really bad time complexity. It means that it's going to take your computer longer to do things the higher the value is. So if we put in 50 right here and we run this, you're going to see it's going to take my computer a little bit longer to do this one. And frankly, it might just be like an insanely long time and we might be sitting here forever. So I'm just going to stop this. Let's do Fibo of 10. It should still be able to do 10 relatively quickly. There you go, 55. Let's do 14, 377. Let's bump that up to 20. It can do that pretty quick, 67, 65. If we go up to 30, How fast can you go? Okay, it slowed down a little bit, 832,000. We booped this up to 40. It's going to take a while. So you can see it scales incredibly quickly. We were fine. You go up a little bit more, and it just takes an insanely long time. And this is why there's sometimes where using recursion is not good. And it's not always recursion. Yeah, you don't want to iterate 7 trillion times either. But you can just see the time complexities get a little bit funky here. And as you can see, this is still running right now. It is trying really hard to find the Fibonacci number of 40. So you know what? We're going to let that run. I'm going to let that go. And meanwhile, we're going to work on our next little example, which is drawing some trees. And that's pretty fun. Drawing trees is always a good time. And we're going to do this with turtle, obviously. So let's come up here and do a nice little import turtle here, as we do. And then we're going to make some trees. So let's define our recursive function here as tree. We're going to pass in the number of branches that we want on our tree. Then it's the number of times. Hey, the 40 just finished. So here you go. There's your value, 102334155. So as you can see, that takes a little bit of a while to do. So there's the Fibonacci stuff. But let's move on to some trees. You're going to find this insanely cool, I'm sure. So n is the number of times we're going to recurse, and then we need a size of the tree branch. Okay? And this will make sense shortly as we continue on. So we have this. Then we need to actually draw the tree. So this is where we're going to do some turtle magic here. Let's do turtle.forward. And we're going to go forward the size of the branch. And then we're going to turn turtle.left. And we're just going to turn at a 25-degree angle. Okay? Then we're going to recursively call tree. And we're going to say, okay, so do n. But we're going to do n minus 1. Okay? And we're going to do size divided by 2. So this is going to shrink down the size of the tree. And don't worry about n, because I'm going to put in what makes this recursive call actually end, because we've seen the recursive calls end up here because we're subtracting n, and it eventually hits 0 and 1. These are your base cases, and we're going to need a base case here as well, and we're going to put that in at the end. So here's our recursive call, tree of n minus 1 size divided by 2. Then I'm going to do a turtle.right, and we're going to go right 50 degrees, which is going to go, so right now we're going up, we're turning to the left 25, and then we're going to turn to the right 50, so it's going to go 25, which is going to put us back straight up and down. Then we're going to go another 25, which will bring us to the right here. This makes more sense if you're taking geometry, but I promise you it's not too bad here, and you'll see exactly what I mean when the picture is drawn. After we go right, we want to do another recursive call. So we're going to do the same thing here, calling tree on n minus 1 size divided by 2. Then we're going to go back to where we were, and then do a turtle.back, which is going to bring us backwards of our size. It's just to put it back to the initial marker where he was. So this is all it's going to take to draw trees here. We just need our recursive call, our recursive base case. So if n is equal to 0, then we just want to pass. And pass just means don't do anything else here. Just move on. So elif num is greater than 0, then we want to do all of these. And I'll highlight these and tab these over to keep the white space going in Python. And this is actually just n because I am an idiot. Okay, so we can call this here, and you will see everything work totally fine. There is nothing here that is tricky. There's nothing here that's doing anything spectacular. Let's define a main function. I'm going to turn the turtle 90 degrees to the left, which will put him straight up and down, because he normally faces to the east. He'll face this direction. So we're going to instead turn him 90 degrees so he's facing up instead. And then if we just do tree of 2 and 100, this is going to draw our tree for us. And if we run this here, oh, this is going to run the Fibonacci sequence. We don't want that. Get rid of Fibo here and instead call main, please. So we run this. It's going to open up our turtle window. He's going to go up, and he's just going to draw a very simple tree. And you saw that occur. We have to add in a turtle.done so this guy stays on the screen. We'll do that again real quick. You should be able to see this. You absolutely can. Okay, so let's look at this. We saw what that looked like. My cursor is spazzing out on the screen right now. Let's go back to the code here, which we should be able to do just by closing this window. Okay, there we go. We go back to the code. Let's walk through what this is doing. Okay, we're passing in n is 2. We're passing in a size of 100. So if n is equal to 0, pass. It's not. So elif n is greater than 0, we're going to go forward size. So we're going to go up the amount here, okay? And then we're going to go left 25 degrees. So it's going to turn this guy 25, and then it's going to call tree of n minus 1 and size divided by 2. So size is now going to be 50, and n is now going to be 1. So then it's going to go, it's going to recall this. If n is equal to 0, it's not, so it's going to be 1. So we're going to go down, and it's going to go forward size, okay? So it's going to go forward size. It's going to go forward half of what size was. So it's going to go forward 50. That's why that tree branch is a little bit less than our main one. It's half of our main one. Then it's going to go, and it's going to call tree again. And it's going to go, and n is going to be 0. So it's going to get to here. It's going to say n is equal to 0. Okay, pass. So go back. So now we're going to go back to the original, which is going to put us here because that recursive call is over. That was occurring here. So turtle.write 50 is going to turn our guy 50. And then it's going to go, okay. So tree of n minus 1 size divided by 2. So n right now is 2 because we're still in that initial recursive call. So tree of n minus 2, a size of half. So we're going to be passing in 2 minus 1, which is 1. And then 50 because that's 100 divided by 2. It's going to go, it's going to recursively call. N is equal to 1, so it's not going to pass. It's going to go forward half of size, which forms our other branch. And then it's going to go, and it's going to go left 25. And that's going to be it. Like, it's just going to end because we then recursively call again. And that's it. We're done. It equals 0. So it's going to get to here. It's going to go back 25. And it's going to go back the size we came. And it's going to be all good. You can recursively call this a ton of times. And I want to do it to show you guys. So let's recurse this 4 times. Well, we'll recurse it 3 times here real quick. We run this and you can see it goes up, left, and then it's going to fork out again because it's going to recursively call that again and go out that way that time. Let's do this with 4. And you're going to see shortly, we're going to be creating some pretty dope looking trees. So it's going to go out and it's going to do all of these little recursive calls at the end there to create a beautiful tree. We do this with 5. It's going to make one even more intricate and more cool. So we'll keep it going. It's doing tiny, tiny little branches. Hold me closer, tiny branches. And it just looks really, really good. We're just drawing some trees. And this is all just being done using recursion. So I know what you want me to do. You want me to sit here and put this at like 100. I'm telling you right now, you're going to be severely disappointed. Because all this is going to do, it's going to continue to curve, and then it's going to get so tiny because size is getting divided by 2 each time we recurse. So this is just going to sit here, and it's drawing that. Don't worry. But you're going to be here for the rest of the day if you want to watch this. We could make the turtle speed 0 here. So turtle.speed as 0, and this will speed it up significantly. But when I say speed it up significantly, we're still going to be here forever. Recursively calling this 100 times, it's never going to finish. Like, you could sit here for the rest of the day. You will not see this finish because it's just going to recursively call that over and over and over and over again. It's insanely slow. The time complexity is really bad. The bigger the number gets, the slower this goes. We could do 10. If we do... not speed of 10, but if we do a call of 10, it's going to look very intricate and pretty, but it will finish eventually. And you can see it's like borderline at the same spot it was last time here in half the amount of time. It's already building a different branch. is very, very tiny. And you can see that pretty blatantly here, but it will build this tree. It will enjoy building this tree. This is straining my computer to do this, but I mean, it's all for the meme here. But this will draw this tree, and it will do a nice little recursive call. So hopefully that taught you guys a little bit about recursion. I completely understand. Recursion is an incredibly difficult thing to wrap your head around. You might be walking away from this video being insanely confused. I don't think that I, in any way, shape, or form, taught this to the degree that it should be taught. It's incredibly difficult for me to teach because there's a lot of times where recursion still doesn't work in my head. But there are a lot of times where it's insanely useful to use. And I'm sure that you will come across situations and scenarios in your code where you want to use recursion to solve problems. And you can do all kinds of drawings with Turtle with recursion. If you just Google Turtle recursion, there's a lot of weird, funky designs that you can make using Turtle and recursions. So look it up, have some fun with it. Try to wrap your head around what's going on. I recommend taking a sheet of paper and writing out what's going on and solving those problems that require recursion using some written logic. But that's going to do it. Thank you guys so much for watching. Thank you for the support on the series. I'm enjoying making it, and I'm going to continue to pump out these videos for you guys. I know there's a couple of you that are really, really enjoying this series. So thank you so much for watching, and I'll see you guys in the next little video. Bye-bye.